Hey everyone, and welcome back for another deep dive. Today we're going to be tackling something pretty mind-bending, the symphony of the universe.
Ooh.
We're going to be exploring how energy and structure work together on a cosmic scale.
Okay.
And get this, we're going to be using something called the Hamiltonian as our guide.
What's really fascinating about this deep dive
Yeah.
is you've given us this mix of, like, scientific papers
Right.
and philosophical reflections.
Yeah. I'm excited to see where this goes.
It's a little unusual.
Yeah.
Not your typical astrophysics deep talk.
Yes, for sure.
First things first.
Okay.
What exactly a Hamiltonian?
Okay.
I get that it's an equation,
Yeah.
but what does it actually tell us about the universe?
So imagine you have a system,
Yeah.
and this could be anything from a single atom
Right.
to the entire universe.
Wow.
The Hamiltonian is like a master equation that describes
Yeah.
the total energy of that system.
Okay.
And it doesn't just list the energy.
It connects potential energy, the
Right.
kind that's stored up,
Yeah.
with kinetic energy,
Okay.
the energy of motion.
So it's
Yeah.
like a cosmic energy balance sheet,
Okay.
showing how these different forms of energy are interacting
Exactly.
and influencing the system's behavior.
Exactly. And what's incredible is that this single concept,
Yeah.
the Hamiltonian, can be applied to something as tiny as an electron orbiting an atom,
Right.
or as vast as the universe itself.
Okay.
It shows us that there's this underlying structure to how energy works, regardless of scale.
Okay. So that's starting to make a little bit of sense.
Okay.
Now,
Yeah.
on to one of the big mysteries of the universe.
Yeah.
Dark energy.
Dark energy.
We've all heard the term,
Yeah.
but honestly, it sounds kind of like science fiction to me.
It does sound like something out of a movie.
What is it?
Yeah.
And why should we care about it?
So dark energy makes up about 68% of the universe's total energy.
Wow, that's a lot.
And it's thought to be responsible for the accelerating expansion of the universe.
Wait a minute. The universe is expanding. I thought it was already huge,
It is huge, and it's getting bigger all the time.
Oh, wow.
So for a long time, scientists thought that the universe's expansion was slowing down
Is gravity.
due to gravity, yeah.
Right.
But observations in like the late 1990s showed that the expansion is actually speeding up.
So it's like something is pushing the universe apart,
Right.
working against gravity. And that something is dark energy.
That's the leading theory.
Okay.
Einstein actually came up with the concept,
He did.
though he called it the cosmological constant.
Whoa.
He envisioned it as like a constant energy density throughout space
Okay.
that counteracts the pull of gravity.
So if the universe is constantly expanding
Yeah.
at an accelerating rate,
Right.
does that mean it will just keep getting bigger forever?
Well,
That's-
that's where things get really interesting.
Right.
And where those different theories about the universe's ultimate fate come into play.
Okay.
So
where?
will it keep expanding forever,
Right.
or will it eventually reach a breaking point? Scientists are still trying to figure that out.
Yeah.
And dark energy is a key piece of the puzzle.
So understanding this dark energy stuff is really important.
Absolutely.
It's not just some abstract concept.
Mm-hmm.
It has massive implications for the future of the universe.
It does.
Right.
And then there's dark matter.
Okay.
It's another invisible force.
Okay.
But instead of pushing things apart,
Yeah.
it's thought to be holding things together.
Right. Dark matter.
Yeah.
I remember reading in one of the articles that it's like the scaffolding of the universe. Can you explain what that means?
So imagine you're building a giant skyscraper.
Okay.
You need a strong framework
Yeah.
to support all the visible elements, the
Yeah.
walls, the floors, everything. Dark matter is kind of like that framework for the universe, that underlying structure.
So even though we can't see it directly,
Right.
dark matter is essential for the formation of galaxies and the large-scale structure of the universe.
Exactly.
So it's exerting gravity, just
Yeah.
like ordinary matter,
Just like ordinary matter.
influencing how galaxies rotate and cluster together.
Exactly.
And here's the thing. Dark matter makes up about 27%
That's right.
of the universe's mass and energy.
Yeah, about 27%.
That's way more than I would have guessed.
It's
So
odd.
if we can't see dark matter,
Yeah.
how do we even know that it's there?
So we can infer its presence through its gravitational effects on visible matter.
Okay.
For example, galaxies rotate faster than they should, based on the visible matter that we observe.
Okay.
That extra gravitational pull is attributed to dark matter.
It's like trying to understand a ghost by the way it makes objects move around it.
That's a great analogy.
Yeah.
So scientists are constantly developing new techniques to try and detect dark matter directly.
Okay.
But for now, we rely on its gravitational fingerprint to map its presence.
It's amazing to think that most of the universe is made up of stuff that we can't even see.
Right.
It makes you wonder what else we're missing.
What are we missing?
What else is out there that we don't even...
We haven't even begun to imagine.
Yeah.
Yeah.
So speaking of the stuff that we can see, what about the everyday matter that makes up stars, planets, us, all that good stuff?
Yeah.
What is that?
So that's called baryonic matter.
Okay.
And it accounts for a surprisingly small percentage of the universe.
Really?
Only about 5%.
5%?
5%.
So all the stars?
Yeah.
Galaxies.
It's mind-blowing.
Everything we can see with our telescopes is just a tiny fraction.
A tiny fraction.
Of what's actually out there.
Of what's actually out there.
That's a wild. But even though it's a small percentage, you're saying that baryonic matter is still incredibly dynamic.
Yeah, so it's kinetic energy.
Okay.
The energy of motion. That's what drives all the visible action in the cosmos. Star formation, supernova explosions, the swirling of galaxies, everything.
So it's like the universe is putting on this dazzling light show.
Yeah.
And we're only seeing
a tiny glimpse.
A tiny glimpse of the backstage action.
Okay. Now, speaking of mind-boggling. Let's dive into something that one of your sources really emphasized.
Okay.
The idea that the entire universe might behave like a single giant quantum system.
Oh, wow. Okay, so we're talking about quantum mechanics. I read a little bit about it.
Yeah.
I'll admit, it always makes my head spin a little bit.
Yeah.
How could some
it's a radical concept.
As vast as the universe be governed by the same rules that apply to tiny particles?
So the idea is that the same principles that govern the behavior of atoms and subatomic particles.
Okay.
Like the principles described by Schrödinger's equation and the Hamiltonian operator might also apply to the universe as a whole.
But wait. Doesn't quantum mechanics deal with things that are uncertain and unpredictable?
That's right.
How can we even begin to apply those ideas to the universe on such a massive scale?
That's the challenge and the beauty of it.
Okay.
It requires like a whole new way of thinking about the universe.
Okay.
One that embraces uncertainty and the interconnectedness of everything.
Okay, this is where I need to hold on tight.
Yeah.
Because I feel like we're going down the rabbit hole.
Yeah.
If the universe really is a giant quantum system, what are the implications? What does it tell us about our place in it?
That is a question for the ages.
Right.
And it's something that we'll explore more deeply in the next part of our deep dive.
Okay.
We'll unpack what it means for our understanding of free will.
Oh, wow.
Consciousness.
Okay.
And even the nature of reality itself.
I have a feeling this is going to be a wild ride.
Hold on tight.
I've been ready for it.
Because it's about to get even more interesting.
But before we jump to those big philosophical questions, let's delve into some more concrete stuff from the source material.
Yeah.
The idea of mesoscale coherence and these fascinating geometric structures that they were talking about.
Yeah, this is where those recursively scaled dodecahedrons come in.
Oh, yeah.
Now, I know that sounds like a mouthful.
Okay, break it down for us.
But bear with me.
I'm sure our listeners are thinking the same thing.
Okay, so imagine a dodecahedron.
Okay.
Which is a 12-sided geometric shape.
Okay.
Now, imagine that each of its faces is made up of smaller dodecahedrons.
Okay.
And each of those smaller dodecahedrons is made up of even smaller ones.
Okay.
And so on in this never-ending fractal pattern.
So it's like a Russian nesting doll of dodecahedrons.
Precisely.
With each level containing smaller versions of itself.
And these recursive structures are more than just mathematical curiosities.
Okay.
They're being used to model how information is integrated.
Okay.
And processed in complex systems.
So
it's like how our brains process information by connecting different levels of neural networks.
I'm starting to see how this connects to the idea of mesoscale coherence.
Right.
It's about how interactions at intermediate scales, not too big and not too small, can have a huge impact on the behavior of the entire system.
And the study you provided actually ties these dodecahedrons and mesoscale coherence to that formula you mentioned earlier.
Oh, yeah.
T equals H times B.
Yeah, that formula. Yeah. I remember seeing it in the source material, but I'll admit it went over my head a bit.
Okay.
Can you refresh my memory on what that means?
It breaks down like this. T represents the observable phenomena.
Okay.
The things that we can see and measure.
Okay.
H is the Hamiltonian. That master energy equation we talked about.
Right.
And B stands for perturbations,
Okay.
little nudges or changes that affect the system.
So this formula is saying that the things that we observe in the universe
Exactly.
are a result of the system's energy, the Hamiltonian, being influenced by these perturbations.
Exactly. It's a way of understanding how even tiny changes can have like a ripple effect throughout a system.
Right.
Especially when those changes occur at like crucial points of connection.
Okay, so I'm starting to see the connection back to the dodecahedrons.
Right.
The way those structures are organized.
Yeah.
With smaller structures nested within larger ones, creates multiple levels of interaction and feedback.
Right.
Okay.
And the study suggests that the specific geometry of these dodecahedrons, the way they're recursively scaled, has a direct impact on how information flows and changes within the system.
So this is getting pretty complex.
It is.
But I think I'm getting the gist of it.
Cool.
What are the real-world implications of all this?
Okay.
Does this just apply to, like, abstract mathematical models?
So that's the exciting part. It's not just theoretical.
Okay.
These ideas about mesoscale coherence and geometric structures are finding applications in cutting-edge technologies.
Okay, like what?
Like optomechanical circuits.
Okay, what are those?
Which use light and tiny vibrating mirrors to achieve incredible precision in measurement and control.
Wait, are you saying that these abstract mathematical models are being used to build real-world devices?
Yeah, and it goes beyond optomechanical circuits.
Okay.
Researchers are also exploring how these concepts apply to phonic waveguides, which manipulate sound waves at incredibly small scales.
Wow.
And even to biological systems like our own bodies.
Whoa.
Yeah.
That's mind-blowing. It sounds like we're on the verge of some incredible breakthroughs.
We are indeed.
In technology and medicine, all thanks to these seemingly abstract mathematical concepts.
And what's even more fascinating is how these ideas are bridging the gap between science, technology, and even spirituality.
Now, that's a topic I'm really interested in exploring further. So we've covered a lot of ground already.
Yeah.
From the mysteries of dark energy and dark matter to the mind-bending realm of quantum mechanics and these recursively scaled dodecahedrons.
And we've only just scratched the surface.
Yeah.
In the next part of our deep dive, we'll delve deeper into those real-world applications. We'll explore the intersection of science and spirituality and try to answer that ultimate question. What does it all mean?
I can't wait. This is definitely a deep dive that's making me think about the universe in a whole new way.
Until next time, keep those cosmic questions going.
Welcome back to our deep dive into the symphony of the universe. Last time we left off with this mind-blowing idea that the entire universe might behave like one giant quantum system. And we even touched on these fascinating recursive geometric structures called dodecahedrons.
We also explored how this mathematical formula T equals H times B helps explain how even tiny perturbations or nudges can create ripple effects throughout a system, especially ones with interconnected structures like those dodecahedrons.
Right. And we tease that these abstract ideas actually have real-world applications.
They do.
So let's dive into that. You mentioned something called optomechanical circuits.
Yes.
What are those exactly, and how do they connect to everything we've been talking about?
So optomechanical circuits are devices that combine light optics and mechanical motion. So picture this: tiny mirrors so small you need a microscope to see them.
Wow.
Are carefully designed to vibrate at specific frequencies. These vibrations interact with light particles called photons in a very controlled way.
So I'm picturing these tiny mirrors doing a sort of dance with light.
Yes.
But how does that translate into something practical? What's the point of making these tiny mirrors vibrate?
The key is that the light and the mechanical motion are coupled together. They're synchronized. Working in harmony. This allows for incredibly precise measurements and control over the system.
So it's like having a super sensitive instrument that can detect the tiniest changes in energy or motion.
That's a great way to put it. And because these systems are so sensitive, they have huge potential in a variety of fields.
Like what? Give me some examples. I'm really curious to see how this connects to the real world.
So one of the most exciting applications is in quantum sensing. These optomechanical circuits can detect incredibly subtle phenomena, like gravitational waves.
Wow.
Those ripples in space-time predicted by Einstein. Or tiny fluctuations in magnetic fields, which could revolutionize medical imaging.
So it's like having a microscope for the universe's most subtle whispers.
Exactly.
Okay, so we're using light and tiny vibrating mirrors
Yeah.
to listen in on the secrets of the cosmos.
Precisely, and the potential applications go beyond just sensing.
Okay.
These circuits can also be used in signal processing,
Okay.
enabling the development of super-fast optical switches for telecommunications.
Okay, now you're talking my language.
Yeah,
Faster internet, more powerful data transfer.
right.
That's something we can all get behind.
Absolutely. And what's fascinating is how the Hamiltonian
Right.
and that T equals H times B formula we discussed
Right.
plays a crucial role in understanding and designing these optomechanical circuits.
Remind me how those connect again.
So remember, the Hamiltonian describes the total energy of a system.
Right.
In this case, it would describe the energy of the light, the mirrors, their interactions, everything.
Okay.
It's like the conductor's score for this microscopic orchestra.
I like that. Okay. And
Yeah.
T equals H times B helps us understand how those tiny vibrations,
Yes.
those perturbations in the mirrors,
Mm-hmm.
influence the system's overall behavior.
Precisely by controlling those perturbations.
Okay.
The frequency and amplitude of the vibrations, we can manipulate the circuit's behavior with incredible precision.
So we can make it more sensitive.
We can make it more sensitive, more efficient, and tailor it for specific applications.
It's amazing to think that something as abstract as the Hamiltonian,
It is.
this mathematical concept for describing energy, is now being used to build real-world devices that could change our lives.
And speaking of real-world applications,
Okay.
let's move on to another technology that's influenced by these concepts.
Okay.
Phononic waveguides.
Phononic waveguides. Okay, that sounds intriguing. Bring it down for me.
Right.
What are phonons and what do these waveguides do?
So think of phonons as the sound equivalent of photons.
Okay.
They're the quantized units of sound energy, just like photons are the quantized units of light energy.
So instead of tiny mirrors dancing with light,
Uh-huh.
we have sound waves zipping through these waveguides.
You got it. And these waveguides allow us to manipulate those sound waves at incredibly small scales,
Okay.
like on the level of microchips.
Okay, I'm following so far, but what's the practical use of manipulating sound waves at such a tiny scale?
So one of the most promising applications is in thermal management,
Okay.
controlling heat flow in densely packed electronics.
Oh, that's a big one. Our devices are getting smaller and more powerful all the time,
Yeah.
but heat is a major limiting factor.
It is.
Are you saying that these phononic waveguides could help keep our gadgets from overheating?
That's exactly what they're being developed for.
That's definitely a hot topic.
It is.
And I'm guessing it has implications beyond just keeping our smartphones cool.
Absolutely. Phononic waveguides also hold promise for quantum communication,
Okay.
potentially facilitating the transfer of quantum information in future quantum networks.
Quantum networks. Okay, now we're talking next level stuff. What would that even look like?
It's still early days,
Yeah.
but imagine a network where information is transmitted not as bits, zeros, and ones.
Right.
Right.
But as quantum states, which can exist in multiple states simultaneously.
Okay.
This would allow for ultra-secure communication and incredibly fast computation.
So these phononic waveguides could be the backbone of a whole new kind of internet.
Potentially, it's a whole new realm of possibilities.
Wow.
And remember that concept of mesoscale coherence we discussed earlier?
Right?
It plays a crucial role in both optomechanical circuits and phononic waveguides.
Right. Mesoscale coherence. The idea that interactions at intermediate scales can have significant impacts
Yeah.
on larger systems.
Mm-hmm.
It's like how the behavior of individual cells can influence the health of an entire organism.
Exactly. By understanding and controlling those mesoscale interactions in these technologies, we can optimize their performance and unlock their full potential.
I'm starting to see a pattern here.
Yeah.
It's like the universe has given us these building blocks,
Uh-huh.
light, sound, matter,
Mm-hmm.
and even the laws of quantum mechanics,
Right.
and we're learning to assemble them.
Yeah. In increasingly sophisticated ways
Mhm.
to create technologies that were once considered science fiction.
That's right.
Now let's bring this a little closer to home.
Okay.
We've talked about the cosmos,
Yeah.
about technology,
Uh-huh.
but what about us?
Right.
We're part of the universe too.
We are.
How did these concepts apply to biological systems?
That's a fascinating area of exploration.
Yeah.
Our bodies are incredibly complex systems with countless processes happening at different scales,
Right.
from the molecular level to the organ level.
Yeah.
Mesoscale coherence suggests that the interactions between cells, tissues, and organs
Right.
play a vital role in our overall health and functioning.
So it's like those recursively scaled dodecahedrons,
Exactly.
but the structure and the interactions between different levels
Mhm.
influence how information flows and changes within the system.
Precisely by understanding those mesoscale interactions in our bodies,
Okay.
we might unlock new approaches to medicine,
Okay.
diagnostics, and even tissue engineering.
This is starting to sound like the plot of a sci-fi movie.
Yeah,
Manipulating cells and tissues with light and sound.
it's real science.
Wow. Okay, but you're saying this is real science with real potential.
It is real science, and the potential is enormous.
Oh.
Think about using light to target and destroy cancer cells, or using sound waves to stimulate tissue regeneration.
Wow, the future of medicine could be more incredible than we can imagine.
And just like with optomechanical circuits and phononic waveguides,
Yeah.
the Hamiltonian and T equals H times B can help us understand
Right.
the energy dynamics and the effects of those tiny but crucial perturbations within biological systems.
Wow. Okay, this is blowing my mind.
Yeah.
We've gone from the vastness of the cosmos
Right.
to the intricate workings of our own bodies.
Right.
It really highlights the interconnectedness of everything in the universe.
It does, and that interconnectedness extends to the tools we use to study and understand the universe.
Okay.
Remember you sent us some information about the quantum Fourier transform?
Vaguely refresh my memory on that one. What is it and why is it important?
So it's a mathematical tool, a key ingredient in quantum algorithms, like Shor's algorithm.
Okay.
It's pretty complex,
Yeah.
but in essence, it allows us to perform certain calculations exponentially faster than classical computers can.
Okay, so we're talking about quantum computers now.
Now we're talking about quantum computers.
I know they're supposed to be incredibly powerful,
Yeah.
but I don't really understand how they work.
So it's a deep topic, but in a nutshell,
Okay.
quantum computers exploit the weirdness of quantum mechanics
Okay.
to perform computations in a fundamentally different way than classical computers.
Okay.
And the quantum Fourier transform is a key piece of that puzzle.
So what are the implications of this? Why should our listeners care about quantum computers and this quantum Fourier transform?
So one area where it could have a huge impact is cryptography and secure communication.
Okay.
Shor's algorithm,
Mm-hmm.
which relies on the quantum Fourier transform,
Right.
has the potential to break the encryption methods that protect much of our online data today.
Wait, so quantum computers could make all of our passwords useless?
It's a double-edged sword.
That sounds a little scary.
On the one hand, it could pose a threat to cybersecurity as we know it.
Right.
But on the other hand, it could also lead to the development of new unbreakable encryption methods
Okay.
that could protect our data in the future.
That's a relief.
Though it sounds like the race is on
Yeah.
to develop quantum-resistant encryption
Right.
before these powerful computers become widespread.
And what's fascinating is how the quantum Fourier transform connects seemingly disparate fields.
It does.
Quantum mechanics, signal processing, and even computer science.
Yeah, it's like the universe is speaking a universal language,
Uh-huh.
and we're finally starting to understand the grammar.
So this brings us to, I think, a really critical point in our deep dive,
Okay.
the interception of science, technology, and spirituality.
Right.
We've explored the Hamiltonian, those fascinating geometric structures, and even the potential applications of mesoscale coherence.
We've seen how these ideas are shaping cutting-edge technologies,
Right.
revolutionizing our understanding of the universe,
Yeah.
and even influencing how we think about ourselves.
But where does the spiritual dimension fit into all of this?
That's what we'll explore in the final part of our deep dive.
Join us as we continue our journey through the symphony of the universe. Welcome back to the final part of our deep dive into the symphony of the universe. It's been quite a journey, hasn't it?
We've covered a lot of ground, from the vast cosmic scales of dark energy and dark matter to the mind-boggling world of quantum mechanics.
Right.
We even explored how these concepts are shaping cutting-edge technologies
Yeah.
and might even revolutionize our understanding of biological systems.
We dove deep into those fascinating recursive dodecahedrons,
Yeah.
learned about the magic of optomechanical circuits, and even explored the potential of phononic waveguides.
Right.
But now we arrive at, I think, the biggest question of all. What
Yeah.
does it all mean?
It's the question that drives so much of human inquiry, isn't it? We can explore the how,
Right.
the mechanics of the universe,
Right.
but the why is what truly captivates us.
Yeah.
That's the purpose of this grand cosmic dance.
It's a question that has echoed through philosophy, religion, and science for centuries.
Centuries.
And while we might not find a definitive answer, our exploration has certainly brought up some thought-provoking ideas.
It has.
One of your sources, a philosophical piece, really resonated with me.
Okay.
It proposed a connection between the universe's Hamiltonian, that master equation governing the universe's energy,
Yeah.
and the concept of divine order.
So it's suggesting that there's an underlying intelligence,
Right.
a grand design
Yeah.
woven into the very fabric of reality.
It's a beautiful concept, isn't it?
It is.
Imagine the universe as a symphony with the Hamiltonian as the musical score.
Yeah.
But who is the composer?
That's a question that has intrigued philosophers and theologians for ages.
Right.
And while science might not have a definitive answer,
Yeah.
it offers tantalizing hints.
Okay.
The interconnectedness we see at all scales, from quantum entanglement to the cosmic web,
Right.
points toward a unity, a wholeness that transcends individual parts.
So, like, every note in the symphony contributes to the overall harmony.
Exactly.
Every element in the universe plays a role in the grand scheme of things.
And that includes us.
Right.
We're not merely passive observers of this cosmic dance.
Right?
They're active participants.
Yeah.
Our thoughts, our actions, even our very existence
Right.
contribute to the unfolding symphony of the universe.
That brings to mind the idea of mesoscale coherence.
Yes.
How interactions at an intermediate scale can ripple throughout a system.
It's a powerful concept, isn't it?
Yeah.
Our individual lives might feel small in the grand scheme of things.
Right.
But every choice we make, every interaction we have creates a cascade of effects that reverberate throughout the web of life.
It's almost as if we're all composing our own melodies within the larger symphony.
And this raises another profound question. If we entertain this notion of a divinely ordered universe, does that imply our lives have a predetermined purpose?
That's a question that delves into the age-old debate of free will versus determinism.
Exactly. But if we consider the possibility of the universe as a giant quantum system,
Right.
perhaps it's not a matter of either,
Yeah.
but rather both can.
Are you suggesting we might have free will within a framework of universal laws?
Perhaps. Think of it like improvising a solo
Okay.
within the structure of a musical composition.
Okay.
You have the freedom to express yourself,
Right.
to explore different notes and rhythms,
Right.
but you're still playing within the harmony and structure of the piece.
So maybe the meaning of life isn't about reaching a fixed destination,
Right.
but embracing the journey itself.
Exactly.
The unfolding of our unique experiences, our interactions,
Yeah.
our contributions to the symphony.
It's a beautiful way to think about it, isn't it?
Yeah.
The purpose isn't necessarily predefined, but emerges from the interplay of our choices and the universal forces at play.
So what does that mean for us here and now?
I think it invites us to approach life with a sense of wonder and awe,
Okay.
to recognize the interconnectedness of everything,
Right.
and to embrace the mystery of it all.
To listen for those subtle harmonies within the symphony.
To remember that we're not just observers, but composers of this magnificent, ever-evolving masterpiece.
As we conclude this deep dive,
Yeah.
it feels like we've journeyed through not just the universe, but through different ways of understanding it.
We've explored the intricate mechanisms,
Yeah.
the philosophical underpinnings, and even touched upon the spiritual dimension.
Right.
It's been a profound exploration.
This deep dive has taken us from the vastness of the cosmos to the intricacies of our own being. We've encountered mind-boggling concepts and pondered questions that might not have definitive answers.
Oh, perhaps the most important takeaway is this. The universe is not a cold, indifferent void. It's a vibrant, interconnected symphony of energy, matter, and consciousness.
And we are all an integral part of that symphony,
We are.
playing our unique roles in this grand cosmic dance.
So keep exploring, keep questioning, keep seeking meaning in the symphony of the universe, and as always,
Keep those cosmic questions coming.